the binomial random variables again, I do have one more handout if someone wants to come get it. So we went through and we kind of looked at how to find the formula for it yesterday. Today we're going to actually tell you the formal requirements for binomial distribution. So your requirements to use a binomial distribution for it to actually be a good fit for your data is that you have to have a fixed number of observations, and all your observations have to be independent, which means they don't affect each other. Okay. Each observation is classified as either success or failure. Okay. So yes or no, success or failure, only two options, which makes it sound like a Bernoulli random variable, but instead of just doing our experiment once, we do it n times. So basically it's a sequence of Bernoulli random variables. And the probability of success, P, needs to be the same for each observation. So every time I flip a coin, the probability of getting heads will be the same. The distribution of the count x of our successes is, we say that has the binomial distribution with parameters n and p, and we say that x is distributed binomially with n and p. So this means is our distribution sign, the little tilde, and b for binomial. This is our probability mass function. This is the formula that we'll use. What does this symbol? The n and the x in the parentheses? It's the combination. Okay, p to the x, 1 minus p to the n minus x. So our n choose x is the binomial coefficient. It accounts for the number of ways in which we can choose k successes from our n observations. It looks like I changed all my x's to k's. I apologize. Okay. So n choose k is n factorial over k factorial times n minus k factorial. P to the k accounts for our probability of getting k successes, and 1 minus p to the n minus k accounts for getting our n minus k failures. So the first thing you have to be able to do for any test or homework is you have to be able to identify if it's binomial, because you can't use the binomial distribution in the formulas unless it's binomial, and on the test I won't tell you if it's binomial, and you won't know that you're working section 3.1 and everything is binomial. So for each of them, we're going to check to see if it's binomial and say what x, n, and p are. So each child of a particular pair of parents has probability of 0.25 of having type O blood. Genetics say that the genes one child gets doesn't affect the genes that the other child gets. If these parents have 3 children, count the number of children with type O blood. Okay, so what do you think? Okay. Do we know in advance how many times we're going to do this trial, or how many people we're looking at? Okay. We know that we have 3 children. Okay. Do we have just 2 options? Could you classify it as just 2 options? What would my 2 options be?
Type O blood or not.
Type O or not type O. Of course, it would be possible to classify this in more ways, like type O, A, type B, but if we classify in just 2 ways, that lets us use the binomial distribution. Okay, let's see, what else do we need? We need them to be independent. It tells us independent. And the last thing is we need a probability of success that stays the same. So what is our probability of having type O? 0.25. And it should be the same for each child. So we're good. So this is binomial. And finally, what would x be? Not as a number, but how are we defining this random variable?
Number of children with type O blood.
Number of kids with type O blood. So for the next one, we have replacement heart valves have a probability of 0.77 of performing well for 15 years. Therefore, the probability of failure for a heart valve is 0.23. Count the number of patients with heart valve failures in a group of 500. Okay. So we go through and we say, okay, do we know in advance how many people we're looking at? 500. Can we classify in just two ways? Failure or not. Okay. Should the patients be independent of each other? Okay. And the probability of having it fail should be roughly about the same for each person. So everything fits, so this is binomial. And x is what? The number with failures. So the next one, we want to draw 2 cards from a standard 52 card deck with replacement. Consider drawing a heart a success. So what is n?
2.
Okay, what are my 2 classifications? Heart or not heart? Okay, should each card draw be independent?
Yes.
Because?
Replacement.
With replacement, we put it back. So the first card doesn't affect the second card. And what is my probability of getting a heart? One-fourth, 0.25, 13 out of 52. Okay, and does that stay the same for each card? Yes, because I put them back before I do another one. So this is binomial. And x equals the number of hearts.
How would we make one of these? Not make one.
I think the next one is. So this time we want to draw 2 cards from a standard 52 card deck without replacement. Consider drawing a heart a success. So we start off and we say, okay, well n is 2. That's a good thing. A heart is a success. I can still say heart or not heart. Okay, so we're still doing good. The next thing I check is independence. Okay, no, because I don't put the card back. And so if I pull 1 heart out the first time, then I have less hearts to choose from. Or if I pull out a not heart, that still don't affect my probabilities. So this is not independent. So, not binomial. Notice as soon as one thing broke down, it was no longer binomial. Now, it's not independent. Also, what's going to happen to the probability? Is the probability of drawing a heart constant? No. And usually, if the probabilities change, that means that they are dependent. And if they're dependent, then that usually means that the probabilities will change. Let's see. So the next time, we decide to roll a dice until we get a 6. We let x be the number of times we have to roll the dice. So what about this one? Okay, so not binomial because, okay, because we don't know n. So again, you have to know in advance how many times you're going to do your experiment. You might get a question that's worded slightly more like 6, so Toss a fair coin 15 times. Give the distribution of x, which is the number of heads you observe. So this is just asking, well, can you tell me if it's binomial or not? And if it is, what is n and p? Okay, so what do you think about this one? Okay, let's go through our checklist. Do we know n? N equals 15. What are my two classifications? Heads or not head? Independence. Should the coin flips be independent? And the probability of heads is 1/2, and it should stay the same for each time. So everything fits, so this is binomial. With n equals 15, p equals 1/2. So number 7, we roll 2 dice and let x be the sum of the values on the dice. What breaks down here?
Is there one observation, or is it that we don't know how many observations?
Okay.
Well, you don't have a fixed value for how many times you roll it, right?
Sorry, can you say it louder?
You don't have a fixed value for how many times you roll it.
Okay. They didn't tell us. Even if I did assume that I'm just rolling it once, though, what else falls apart?
You're doing a sum, so it's not a yes or no answer. There's no 2 options.
So what are my possible values for sum on the dice? It can be anywhere from 2 to 12, so I don't have just 2 options. Yeah. So all the other things, depending on how you read the wording, can fall apart as well, but that is something that definitely falls apart. So x can be anywhere from 2, 3, up to 12, so not just 2 options. Or we are not counting successes. So, not binomial. So any questions so far? Doesn't seem too bad. Of course, we'll throw in a lot more distributions into the mix before we end today. This next one is interesting because what happens is we say, okay, well, suppose an auditor examines a sample of 150 records out of a total of 100,000 records that are available. One issue is whether each sale was correctly classified as subject to their state sales tax or not. Suppose the 800 of the 100,000 sales are incorrectly classified, and we want to count the misclassified records in the sample. Okay. So to start with, do we know how many records we're looking at? 150. What could be my 2 classifications?
Accurate or not?
Accurate or not. The next thing is independence, or does the probability stay constant? Okay, so when you think about this, as I draw out my 150 records, do you think I'm looking at one and putting it back in for consideration? Do you think they're going to look at the same record twice or 3 or 4 times? No, it doesn't make sense when you take a sample to sample with replacement usually, because you're not going to want to sample the same thing twice very often. So this is probably going to be without replacement. And if we're sampling without replacement, then what happens to our independent or dependent? It's going to become dependent. They affect each other. And the probability is going to change. But how much is it going to change? So probability changes. How much do you think the probability is going to change? Okay, so like, let's think about it this way. So what if I want to get my first inaccurate? What is the probability of getting the first inaccurate?
8 out of 1,000.
8 out of 1,000, or I'm just going to write the 800 out of 100,000. Okay, what would be the probability of getting your second inaccurate? 799 out of 99,999. Okay, and the third one would be 798 out of 999,000. Do you think that that little thing is going to make any practical difference to us? Okay. No, and so what happens is if we have a huge population, okay, so my population is this 100,000 records. If your population is a lot bigger than your sample, then you can sample without replacement and still consider a binomial random variable. Because yes, the probability changes, but not enough to make a practical difference. So for all practical purposes, we can use the binomial distribution. Again, that is because my population is much bigger than the sample. So even though we're sampling without replacement, it just doesn't make a practical difference, so we can still use the binomial distribution here.
So there isn't any kind of like lower bound on that. We're just saying for large populations compared to sample size. It's just
It's for large population compared to sample size. So large population. The rough rule of thumb that I've seen in some books, and different books that give different rules of thumb, is that 20 times larger than sample. Now, it's very rare in this class for you to ever know how big your population actually is, but unless like you specifically know that you have a small population, I wouldn't worry about it. It's probably going to be big enough.
okay. So if we don't know, we just assume large that.
Yeah. If it's something like drawing cards out of a 52 card deck, well, that's probably going to make a difference to us. But if I'm asking you to count the number of people in Utah, and even if you sample 1,000 people, that's still not going to make a big difference. So any questions on how you tell if it's a binomial distribution?
I have a question. Just for the test, are we going to have a note card for each type of notes, or are we just going to have to memorize these formulas?
For the test, I will let you bring a piece of note paper front and back, okay, and whatever you want to put on there. So if you want to copy stuff out of the book, if you want to type stuff, whatever.
No card or like
8.5 piece of paper. So like when I took this class 8 years ago and he said we could copy anything, I'd go to the book and I'd copy stuff and shrink it down to like a quarter size, and I could still read it, get a lot on there. Anything you want on a piece of paper. Now let's actually practice finding these probabilities. So for our first example, we have a gas station receives 5 cartons of milk each week. At this station, 75% of the milk cartons are sold before they expire. And of course, I have to throw away the milk that expires. Let X be the number of milk cartons they have to throw away next week. Okay, so your first question is always, well, is the binomial distribution going to be appropriate? Okay, so what's the first thing you want to check? Start telling me yes or no for everything. Okay. We check N. How many milk cartons are we going to be looking at? 5 of them. Okay. Can we classify it 2 ways? So expire or not, good or bad, however you want to write it. What about independent? Should one milk carton affect the next one? No, so independent. And the probability of having to throw one away since we are counting the number of cartons they have to throw away, what's the probability of throwing one away? 0.25. That should be constant, so yes, we can use the binomial. So now we're going to do a probability. So what is the probability that 2 of your 5 milk cartons expire? So we are looking for the probability that x equals 2. Now I know we've turned the page and you don't have the formula in front of you, so I'll rewrite it for you. So what this means is I say, okay, well I have 5 milk cartons, I need to choose 2 of them to expire. The probability of expiring is 0.25, and I need 2 of them to expire. Then what is the probability of them being good or selling before they expire? That is 0.75, and if 2 of them expire, how many of them have to not expire? 3. Okay. Hopefully you remember where the combination button is on your calculator. I get 0.2636. So there's about a 26% chance that he has to throw away 2 of them next week. Any questions on how we calculated that? What is the probability that less than 2 of the milk cartons expires? So this way I'm looking for the probability that x is less than or equal to 2. What x values does that include? 0 and 1 and 2. So we know the probability of 2. Let's find the probability of 0 and 1. So the probability for x equals 0, well I say, okay, I have 5 milk cartons. I need to choose 0 of them. The probability of expiring is 0.25, and how many do I want to expire? 0. Probability of not expiring is 0.75, and I need 5 of them to not expire. So, 0.2373. Usually if I'm going to be working with probabilities, I'm in the habit of doing up to 4 decimal places. The probability that x equals 1 would be 5 choose 1, 0.25 to the power of 1, 0.75 to the power of 4. .3955. And then we already know from up above that the probability that x equals 2 was 0.2636. So, to find my total probability that x is less than or equal to 2, what do I need to do? Just add them up. .8964. Okay. So there's an 89% chance that he has to throw away 2 or less milk cartons every week.
Wouldn't that just be x less than 2?
Oh, it does say less than 2. This is x less than 2, which means I don't need this. So if I take off the 2, I get 0.6328. So 63% chance that less than 2 milk cartons have to be thrown away each week. So we've done a full problem. Any questions? Usually, like my statistics, 2,000 people complain about this, but after you've taken calculus, that shouldn't be too bad for you guys. So for my next example, Mark has an overall free throw percentage of 70%. He attempts 6 free throw shots, assuming independence. Let X be the number of free throws he makes. Okay. So can we use the binomial distribution? How many times is he shooting? 6. We can say he makes it or not. Until us we can assume independence. And if we can do that, then what is the probability of him making each shot? 0.7. And that should stay constant, since it tells us we can assume independence. Can you think of some things that might mess him up and get rid of that assume independence? He gets mad, he messes one, it gets in his head, or he makes them and then it's going good. But mathematically, we'll assume independence so we can do this problem. So, what is the probability that he'll make 2 shots? Okay, so tell me what to write.
So 6 choose 2. Times 0.7 squared. Times 1 minus 0.7 is 0.3.
Okay? So the probability that he only makes 2 shots is about 6%.
Why did you go to the fourth again?
Okay, so everything has to add up to your number of trials. So if we have 6 trials, if he makes 2 shots, that means he has to miss 4. This power of 4 is when you see on the actual formula says the exponent will be n minus x. So 6 minus 2 gives me my 4. And I realized I should have made this different than the last problem, but find the probability that he makes less than 2 shots. We're looking for x less than 2. So that's going to be the probability that x equals 0 plus the probability that x equals 1. So go ahead, if you have your calculator, try and plug these 2 in and see, or at least write down the formula and see if you get the same thing as me when you're done and when we look up. If you finish before everyone else is done writing, go ahead and try number 4 too. So for number 3, I got 0.010935. Everyone else, did you get that? Any questions if this makes you realize you did something wrong? Oh, oops. So the next one, what is the probability that he will make 5 or more shots? So we're looking for the probability that x is greater than or equal to 5. And so what x values will that entail for me? 5 and 6. Okay, so we need to plug it into our formula. So to get x equals 5, I need to have 6 choose 5. He needs to make 5 of them, which means he has to miss 1 of them. And to get 6 shots, we're going to have 6 choose 6. He needs to make 6, which means he misses 0. .420175. Anyone else? And this next one, what is the probability that he will make at least 1 shot? So we're looking for the probability that x is greater than or equal to 1. Okay. So what x values does that entail? 1, 2, 3, 4, 5, 6, everything but 0. So what's going to make this easier? If I use the complement rule, so 1 minus the probability that x equals 0. And I think we already found that somewhere, didn't we? So 1 minus 0.000729. .999271. Now number 5 should remind you of something we've done before. Have we done problems like this before we knew about the binomial distribution? Okay, yes, before we knew about the binomial distribution, we would have said, okay, we know it needs to be 1 minus the probability that x equals 7. And to get x equals 7, the probability that x equals 7, or 0, not 7, I don't know where 7 came from. We would have said, okay, well that means he needs to miss all of his shots, and the probability of missing is 0.3. He needs to miss all of them, which is 6. So that would give me my 0.000729. So we did know how to do this problem before we learned about the binomial distribution. So we're going to skip 7 because I think that you probably have that I did, but I will work it out and I will put it online as the PDF, or as part of the PDF when I put the PDF up. So you can do it on your own and check and make sure you know how to do it. And the next thing we need to learn about is the binomial mean and standard deviation. So for example 8, if a random variable x has the binomial distribution with n and p, find the mean and standard deviation. So what we're going to do here is we're going to remember the things we learned about the the Bernoulli distribution. Because what happens is we can actually define x as x1 plus x2 plus up to xn where x1 up to xn are Bernoulli random variables. Okay. And anyone remember what the mean and standard deviation were for a binomial or Bernoulli random variable? Can you look back on your previous page? So with mean of p and what was the variance? Next, we can scroll up and look. So the variance was p times 1 minus p. So again, the binomial distribution is really just doing the Bernoulli experiment over and over and over again and just adding your results. Because remember, Bernoulli, it just has a 1 for success, 0 for failure. So if you're counting it, you're just adding up all of your 1s and zeros. So if I want to find the expected value of x for my binomial random variable, then this is really the expected value of my x1 plus all the way up to xn. And what do we know with our rules for expected values? We can just add up each of the individual expected values. So the expected value for each one of my xi's is a Bernoulli random variable, so the expected value is p. So this is p plus p plus p. How many of those p's am I actually adding up? x1 to xn, so I added up n of them. So the expected value for a binomial random variable is n times p. So we're going to use the same method for the variance of x. So we have the variance of x1 through xn. And we know that we can just add up each of the variances if what? They are independent random variables, but if we have a binomial distribution, one of the requirements is that they are independent random variables. So we can write this as the variance of x1 plus the variance of x2 plus all the way up to the variance of xn. And we know that each one of those variances is p times 1 minus p. So the second variance is still p times 1 minus p. Up to the last variance is still going to be p times 1 minus p. And so if I add them all up, how many times do I add them up? N times. So we have n times p times 1 minus p. And that is my variance. Okay. Two very common results that we will use a lot throughout the rest of the class. I'm going to teach you a lot of other distributions. The two that you really need to know when you leave this class at the end of the semester that you actually need to really remember off the top of your head is binomial and normal. Now, the fact that those formulas are so simple means it makes it really easy to actually work with the binomial distribution. So here's an example. In a test for ESP, a subject is shown on the back of a card. The card can be a star, circle, wave, or square. The subject is supposed to name the shape on the card. Each subject looks at 20 cards. Assume each subject is randomly guessing. So does this sound binomial? We know they look at 20 cards. Okay, each card guess can be correct or not correct. They should be independent of each other since they're randomly guessing. And the probability of being correct if you're randomly guessing is going to be 0.25. Okay. Now, even before you knew the formula, if I told you you had a 1/4 chance of guessing anything correctly and you're going to guess 20 times, how many times would you intuitively think you're going to be correct? You would intuitively think you're going to be correct a quarter of the time, so 5 times. And the way you did that is multiply. And our intuition is correct because the expected value is just n times p. So 20 times 0.25 gives me 5. Now this doesn't mean that Susie can't get 4 correct guesses and John can't get 8, but on average each person's going to guess 5 correct. And what is the standard deviation? We don't have a formula for standard deviation, but we know it is the square root of variance. So the square root of np times 1 minus p. So 3.75. Is this a lot easier than figuring out the whole PMF, all of the probabilities, all of the x values, and using the long formula? Okay, much easier, so we really like it when our random variables are binomial.
Is it 3.75 or is it the square root of 3?
Oh, I forgot it's square root, thank you. So 1.936. So for the next example, Nick has a 0.15 probability of bowling a strike on any frame. A bowling game consists of 10 frames. Let x be the number of strikes he gets in a game. So n is 10, p is 0.15. So expected number of strikes is going to be np. So 10 times 0.15 gives me 1.5. So on average, he'll make 1.5 strikes per game. Not too good. And the standard deviation is again going to be the square of n times p times 1 minus p. Any questions on this? Again, then, we're going to go on, and I will fill this out before I put it online so you can check yourself. And if at any time when I say we're skipping this problem, you are more than welcome to say, we want one more, and I will do it, but I think we're okay with skipping it. Go ahead and take your 2-minute break now.